Great. Well, I'm really happy to be here. Thank you for the invitation. Yeah, so today I'm going to talk about the Ruelle invariant and convexity to higher dimensions. So maybe I'll start with the introductory stuff. So let's say that you have a closed three-manifold Y equipped with a smooth flow phi that preserves some smooth measure mu. Then, so in an 85 note, Ruelle introduced this thing, which he did not name, but which now people call the Ruelle invariant, or at least some people call the Ruelle invariant. I'm going to do it like this like root of y phi. And the invariant is the integral of a function on the space y that basically measures the kind of linking of trajectories that are close to each other in the manifold. So what that means is that if I wanted to compute this like little function, little root, at a point y, then to do that, I would flow forward for some large amount of time, so along this trajectory gamma, which is depicted in the picture. And then I would look at some very, very close trajectory, y prime, and I would watch that close trajectory as it kind of wound its way around the trajectory gamma for the same amount of time. And then I would kind of compute like a linking number or a winding number of those two trajectories around each other, divide by some time normalization factor, then take a limit as kind of the time goes to infinity. And that sort of defines this kind of large time rotation quantity associated to any point y. And the Ruelle invariant is essentially just the integral of that function, as long as it's well defined. This, I'm a little, I'm suppressing some choices here, which I'll maybe clarify in a little bit. But roughly speaking, intuitively, this is kind of what this number is measuring. It's measuring sort of an average rotation of the flow phi over the entire space. Okay, so this invariant has appeared in a couple of places since this note. So I guess the note is pretty funny because basically it starts with Ruelle saying, I was not actually going to write this down, but a bunch of people kept bothering me about it. So now I'm going to write this this thing down a little more precisely so people can see it. So originally it doesn't seem like Ruelle thought this was very useful for much. So this kind of invariant appeared in a couple of other places since he wrote this note. So Gamboa Geese has written a lot of stuff about it in low dimensional dynamics. There's been some work on it in other kinds of like mathematical physics, so like bifurcation theory, Sturm-Liouville theory. And recently the Ruelle invariant has kind of started to appear in low dimensional Reeb dynamics, in various settings. So the first one was where Michael Hutchings, who is in the Zoom room, I think, wrote this paper, ECH capacities in the Ruelle invariant, where he basically conjectured a relationship between the Ruelle invariant and sort of the subleading term in an asymptotic expansion of the ECH capacities. So in this paper that he wrote gave some evidence for that in the setting of convex and concave toric domains, or at least some class of toric domains. I don't remember exactly which ones. And then so this kind of relationship with the asymptotics of ECH capacity, or the kind of subleading terms of ECH capacities, has actually very, very recently, like 2 days ago, been at least in a preprint that appeared on the arXiv, been kind of verified for some other set of capacities that are sort of closely related to the ECH capacities. So this relationship with Floor theory, at least in some new class of examples. So this relationship with Floor theory seems to be kind of very, very interesting and something that people are exploring a lot right now. And sort of in a different direction, me and Oliver Edtmair wrote a paper where we used the Ruelle invariant to construct. We used the Ruelle invariant as a method of detecting the difference between so-called dynamically convex contact forms on the sphere and convex contact forms in the sphere. So that was a low dimensional result. And that question of distinguishing those two classes of contact forms was an open problem for a very long time. So that was a really nice application of it. And then also another paper by Dardenis, Gut, and Zhang basically gave new kind of toric examples of dynamically convex but not convex contact forms. So and that was another kind of a follow-up, a paper that built on what we did in our first paper in dimension 3 and 4. Okay, so today what I'm going to spend my time talking about is a generalization of some of the things that appear in these 3 papers to higher dimensions. So the first thing I'll do is I'll just explain kind of a substantial generalization of the 3-dimensional Ruelle invariant to higher dimensional, to like very general higher dimensional setting. And then I'll explain kind of various generalizations of the theorems that appear in these papers. I won't completely generalize some of them, but for the most part, the things I say will be kind of higher dimensional generalizations of some of the results. And then those generalizations are still sufficient for the main application of my first paper with Oliver, which is this theorem that dynamically convex contact forms are not the same as convex contact forms. So I'll talk about that application at the end of the talk. Okay, so the first thing that I want to do is introduce this generalized Ruelle invariant. So what is the input of the generalized Ruelle invariant? What does it take as input data? So the 2 inputs are first a symplectic cocycle for a flow on some compact manifolds equipped with some measure. And then the second piece of data is a homotopy class of trivialization of a certain determinant bundle associated to the kind of bundle of the cocycle. So I'm going to explain what all these words mean right now, but this is the first pass. Okay, so first I want to explain what a symplectic cocycle is. So let's say you have a compact manifold Y equipped with some autonomous flow phi, preserving a measure mu. Then symplectic cocycle for the flow consists of a symplectic vector bundle E and a family of symplectic linear maps from the fiber of E at a point to the fiber of E at that point flowed forward by time t, satisfying the following cocycle property, which is that this basically group property right here, which is equation 1. So I think the best way to think about a cocycle is it's kind of a lift of the flow to the vector bundle, to some vector bundle living over the manifold which the flow is on. And then here the symplectic part is just saying that everything is symplectic. So the vector bundle is symplectic, and the lift of the flow is basically fiber-wise symplectic. So for example, a cocycle E, or a cocycle on the trivial bundle Cn, is just a map from R cross Y to the symplectic group that satisfies this composition property number 1. So that's a simple, so that would be like a matrix cocycle. That's a really simple kind of class of examples. Okay, so that's what a cocycle is. A cocycle is just this linear lift of the flow to the kind of some vector bundle living over your space with the flow on it. Okay, so the second thing I want to say is, what is the determinant bundle? This lambda E. So given a compatible complex structure, for example, which is just a symplectic bundle map from E to itself, satisfying its usual identities. So given that choice, you can associate a complex determinant line bundle to E. So that's just the nth wedge power of E as a complex vector bundle. where the real rank of E is of course 2n. So the space of J is contractible. So this thing is independent of J up to isomorphism. And if the Chern class of E is 0, we can choose a trivialization of the determinative bundle. So that which is just an identification with the trivial bundle. If the vector bundle E is just the trivial bundle, then there's a canonical trivialization, which is just some standard choice of identification. Okay, and so the second piece of input data that we need for the invariant is a choice of homotopy class of trivialization of this determinative bundle. And this set of trivializations is independent of J up to canonical bijection. So that means that, like, even though the kind of lambda E is not itself a well-defined thing without a choice of J, this set is still kind of a well-defined thing to talk about. Like, I can still talk about a trivialization as long as I just talk about them up to homotopy. Okay, so those are the two things we need. We need this cocycle, we need the trivialization. Okay, and then, so now here's like the first main theorem of the talk. So given a symplectic cocycle, phi on E, and given a trivialization tau of the type that I described before, there is a well-defined Ruelle density and accompanying Ruelle invariant. So the Ruelle density is the analog of this kind of rotation function that I described earlier, and it will be some function L1. And then the Ruelle invariant is just the integral of that function with respect to the measure. And it has some properties. So the first property is naturality. So that means that if I have like a symplectic bundle isomorphism and I kind of pull back the cocycle by that isomorphism, then the Ruelle density doesn't change. So this function little rho doesn't change. Second property is direct sum. So if I direct sum, basically, like if I can take the direct sum of cocycles where I like direct sum the underlying bundle and I direct sum the maps. That is accompanied by some operation on trivializations, and the Ruelle invariant is additive with respect to those things. And then the third property is that if I have a trivial bundle, then I can compute the Ruelle density much more explicitly than all of this. And so the way that I do that is I just take the limit as t goes to infinity of the kind of like a lift of this cocycle to kind of the universal cover of the symplectic group, composed with something called a rotation quasimorphism, which I'll explain in a second. But anyway, for the purpose of actually calculating the Ruelle invariant, this last bullet point is kind of the key identity. So I'm going to explain a bunch of examples of this in a second. But the first thing I want to do is just explain rotation quasimorphisms, since they play a big role in the whole paper. So, and maybe people haven't really thought about them very much. So a rotation quasimorphism is, so first it's a quasimorphism. So quasimorphism from some group to R is a map that satisfies the group property up to a constant kind of error term. So that means it satisfies this identity in the definition. And two quasimorphisms are equivalent if their difference is uniformly bounded. So if their difference, if there's some C such that rho of G minus rho prime of G is less than C for every G. So these things are kind of abound in symplectic geometry, and well, maybe not abound, but there's one specific quasimorphism or equivalence class of quasimorphism that shows up all the time, which is something I will call the rotation quasimorphism. So here, first I'll give an example. So let's say you have the map from you can construct a map from the symplectic group to, that should say U1, given by first taking the unitary part of a symplectic matrix under the polar decomposition and then taking its complex determinant. And so now that map lifts to a map on the universal cover. And that map, that lift to the universal cover, turns out is a quasimorphism. So I'll call that one the determinant quasimorphism because I get it by taking the complex determinant of the unitary part. And a rotation quasimorphism on the universal cover of the symplectic group will just be any quasimorphism that's equivalent to R in the sense that I said before. That'll be my working definition for the talk. Okay, so and just to go back to this theorem really quick, so basically what this is saying is that if I give you a rotation quasimorphism, so for example, this one given by the unitary part of the determinant of the unitary part, then I can use that to calculate this little root thing by taking some limit. So this gives a much more explicit way of calculating the Ruelle invariant related stuff, which is also very kind of flexible because I'm allowed to choose any rotation quasimorphism. It doesn't have to be the determinant one that I described before. Okay, so now I'm gonna kind of sketch the construction of the Ruelle invariant, and then I'll talk about a bunch of examples. Okay, so first, here's how you actually construct the Ruelle invariant that satisfies all the stuff in the theorem. So first, you choose an almost complex structure J on E, and a unitary trivialization of the determinant bundle that represents the chosen homotopy class. Then, so given the choice of almost complex structure, you have a fiber-wise polar decomposition of the cocycle. So you can take the maps that appeared in the cocycle, and you can polar decompose them into a map from like EX to EX, and then a unitary map from EX to E phi T of X. So now that you've done the polar decomposition, you can that unitary map will just descend to a map of the determinant lines because it's complex linear. And actually it'll be like a unitary map because it's a determinant of a unitary it's the determinant of a unitary map, so it'll be itself unitary. And under the trivialization, this determinant of the unitary part, this fiber-wise determinant of the unitary part, is identified with some map from R cross Y to U of 1. Okay, and then that map to the circle lifts to a map from the kind of R cross Y to the real line. And then this Ruelle density can just be calculated as kind of some time normalized limit of that lift.
So Julian, just one stupid question. Why do you have an R in the domain of U?
R in the domain. So like big U, so like the cocycle depends on a time and an X. Okay. Yeah. So yeah, and then this thing about the unitary, I mean, this fact that I'm taking the unitary decomposition of a map between two spaces that are not the same is a little weird. But this is like totally something you can do if you think about it a little bit. Doesn't really, the unitary decomposition is some decomposition of maps from like between Hermitian vector spaces. You don't actually need them to be the same. Anyway, so this is basically, this is just how you get the stuff, a thing which satisfies the properties of the theorem. I'm not going to go over the proof that it satisfies all the properties, but so really, I think it's nice to just treat the Ruelle invariant as a black box that behaves in the way described by the theorem and not worry too much about this construction. Okay, so now let me finally get to some examples. So this is kind of where all of these things come from in nature. So first of all, if I have a symplectic flow on a compact symplectic manifold X, so just, you know, a flow that preserves the symplectic structure. Then I have kind of a natural tangent cocycle on the tangent bundle of X. which is just, I just get it by like taking the derivative of the flow and looking at that as a map on the tangent bundle. Okay, and so that flow preserves the measure, the standard symplectic measures, the nth power of the symplectic form. So you get a Ruelle invariant associated to x, associated to the flow phi, and associated to some choice tau in this set of trivializations. Note that the existence of one of these tau is dependent on the vanishing of the Chern class of x. And then, so if phi is Hamiltonian, then I'll just use the notation Ru x h tau instead of Ru x phi tau. But yeah, so Hamiltonian and symplectic flows both give you kind of natural sorts of examples here. Okay, so the next thing is if I have a Reeb flow on a compact contact manifold Y with contact form alpha, then that Reeb flow preserves kind of the standard contact measures. So that's just alpha wedge d alpha to the n-1. And it has a cocycle, which is just the restriction of the tangent cocycle to the contact structure. So the linearized flow of the linearized Reeb flow preserves the contact structure. So this is a perfectly reasonable thing to do. And so this data also has an associated Ruelle invariant, which I'll just call the Ruelle invariant of the contact manifold with tau. Okay, and then so an even more concrete example that is related to both of these is that if I have so let's say I have some star-shaped domain X inside of Cn. And let's say its boundary is transverse to the standard Liouville vector field, which is this vector field Z. Then I can equip X with some canonical Hamiltonian, Hx, which is just the unique Hamiltonian, which is one on the boundary of the domain, and which is kind of satisfies this ODE with respect to Z. So this function doesn't extend, like it's sort of only, it's not going to extend smoothly to 0, but I'm just going to kind of elide that issue for now. So since the Chern class of X is 0, because it's a it's a ball-shaped thing inside of Cn, and also the H1 vanishes, there's basically unique trivialization up to homotopy of Tx. And that means you get a Ruelle invariant, which is just associated directly to X, which is the Ruelle invariant of X with respect to this like specific canonical Hamiltonian. Okay, and then a lemma here, which I'll need later, is that if X is a star-shaped domain, then the Ruelle invariant, like a star-shaped domain of the type I described up here, then the Ruelle invariant is equal to the Ruelle invariant of its contact boundary. So the Ruelle invariant of this special Hamiltonian flow is the same as the Ruelle invariant of the boundary. And also the Ruelle invariant is invariant under symplectomorphism. So this is some symplectomorphism invariant of the Liouville domain. Okay, so these are all like sub-examples, and in particular, the example that I'm going to be most interested in today is this star-shaped domain example. Okay, so so the next thing I'm going to do is kind of give an explicit formula for the Ruelle invariant of a toric domain. So this generalizes some of the results on the Ruelle invariant that appeared in Michael's paper and also the paper by Dardenez et al. So first I'll remind you guys what a toric domain is. So a toric domain x omega inside of Cn with moment region omega inside of this upper kind of orthant of Rn is a domain of the form mu inverse omega, where mu is this standard moment map. So it's this map from Cn to the positive orthant, which takes Z1 through Zn to pi times their norm squareds in each factor. Okay, so in this situation, when I have a star-shaped toric domain, this kind of canonical Hamiltonian can be factored through the moment map. So it can be written as a function just on Rn, precomposed with mu. And here, this function f is the unique function that satisfies the following two properties. Yeah. So when I have a toric star-shaped domain, this H is also kind of toric in the right sense. And now the theorem is that the Ruelle density and the Ruelle invariant of a toric domain are given by the following formulas in terms of f. So first, the Ruelle density is just the sum of the derivatives of f precomposed with the moment map mu. And then the Ruelle invariant is just the integral over the moment domain, so omega, of n factorial times the sum of the derivatives times the standard measure on Rn, just integrated over the moment region. So this is like a super easy formula. Like basically, like hopefully, if I just give you any star-shaped kind of toric domain that you would see in nature, you would have like a pretty reasonable description of its moment region. So this formula basically allows you to just calculate the Ruelle invariant in a really straightforward way. Okay, so as an example, let's take our favorite kind of family of toric domains. So these are ellipsoids. So okay, so the standard ellipsoid, EA1 to EAN, is the toric domain with moment region given by kind of the sort of pyramid shape, or I guess the simplex bounded by some hyperplane and along with all the other axes in the orthant. Anyway, it's the function f for this particular toric domain is given by just the sum over I of xi divided by ai. And the Ruelle invariant is given by therefore is given by this integral. So which I can easily calculate because the function that I wrote down in the theorem is just constant. Yeah, so the Ruelle invariant of an ellipsoid with these kinds of symplectic widths a1 through an is just the product of all these widths multiplied by the sum of their reciprocals. Okay, so that is the example, and then the proof. So let me go through the proof since I think it's really nice and is really pretty elementary. So yeah, okay. So first, so I want to prove this formula for the Ruelle invariant of the any given toric domain. So first, I note that that the moment map mu extends to some toric coordinates on kind of the most of Cn. So on C star to the n. And in these coordinates, the Hamiltonian vector field of the canonical Hamiltonian for the toric domain is given by this formula. So it's basically d theta I, where theta I is these kind of circle coordinates in this chart, multiplied by the derivatives of the kind of defining function f. And I think the way you should think about this is sort of that, like, rotation in the theta I coordinate is sort of like rotation, kind of unitary rotation in the ith C factor of Cn. And so this is basically saying that, like, the vector field sort of rotates, in each kind of C factor in a manner proportional to the ith derivative of the function, and then that kind of rotation is sort of a function of the location on the moment domain. So anyway, so the flow of this vector field is given by basically the phi t of z is z multiplied by some unitary map where the unitary map depends on t and the moment image. So here I give an explicit expression for this unitary this map. So it's basically z multiplied by this unitary matrix, where the unitary matrix is the unitary matrix diagonal entries given by this. And then to compute the Ruelle invariant, I want to differentiate this and then plug it into the kind of a kind of rotation quasimorphism. So when I take the derivative of this family of unitary matrices, I get, or when I take the derivative of this flow, I get this kind of other family of matrices, which is basically an expression for the tangent cocycle. And this will be the same unitary matrix that appears in the flow multiplied by some matrix Q, where Q is sort of a symplectic family of symplectic matrices of the form ID plus T times M of Z. Okay, so now when if I want to compute the Ruelle density, I just take the limit as C goes to infinity of the rotation the determinant quasimorphism multiplied by the lift of this family of matrices divided by T, and then take the limit as T goes to infinity. So by the quasimorphism property of the determinant quasimorphism, I can split this up into two limits. I can split this up into a limit of the determinant quasimorphism on this unitary part and the determinant quasimorphism on this Q part. Now the determinant quasimorphism that I mentioned before is basically just a lift of the complex determinant on the universal cover of the unitary group. So since these matrices U are unitary, that term just turns into the complex determinant. And these, if you looked at the matrix U before, it was just diagonal matrix with e to the I something in each diagonal term. So when I take the complex determinant and then kind of lift it, I just get kind of the sum of the diagonal terms, which turns out to be this. And then the other term actually ends up just going away because this Q matrix is actually a family of shear matrices, and you can show pretty easily that such a family kind of has to have bounded rotation number. Okay, so anyway, the point is when you prove this formula, all you really have to do is, compute very explicitly the kind of flow of this standard Hamiltonian, and then just apply some very standard properties of the rotation quasimorphism. And you don't really have to use you don't really have to open the hood of the Ruelle invariant. You're just kind of like using the axioms in the theorem. Okay, so now we know what the Ruelle invariant is, and we know how to calculate it for toric domains. So so the third thing I want to do today, this is second to last, is discuss the special stuff that happens for a convex Reeb flow. All right, so a star-shaped domain X is called symplectically convex if there is a convex domain X prime inside of Cn that is symplectomorphic to X. So that means, it's something, I'll call something symplectically convex if it's symplectomorphic to something that is convex. Okay, and so it's known that symplectically convex domains have lots of special properties, and there's lots of interesting conjectures about them, like the Viterbo conjecture. And so the second main theorem of the paper is that the Ruelle invariant of symplectically convex domains satisfies a certain systolic inequality. So specifically, let's suppose that let's say little c of x denotes the minimum period of a closed Reeb orbit on the boundary. Then there is a constant depending only on the dimension of the star-shaped domain, or of the convex domain, such that any convex domain satisfies the following inequality. So the product of the systole length, this little c of x, and the Ruelle invariant is bounded above by that dimension dependent constant multiplied by the volume. So this inequality generalizes the upper bound from our previous paper to dimension 4, or from it generalizes it from dimension 4 to any dimension. Okay, so there are a couple of ingredients to this theorem. So I'll go through kind of the three main ones right now. And I'm not actually going to kind of go through the proof in detail. I'll just discuss basically the main points. So the first thing is that the first ingredient to the proof of this upper bound is the following fact. So let's say I have a path of symplectic matrices. Then I say that the path of symplectic matrices is generated by a path of symmetric matrices if the path of matrices satisfies this ODE. So this is just, kind of the obvious thing you would say for any Lie group in any Lie algebra. And then any path based at the identity will represent some element of the universal cover. And if I have a path phi, or if I have an element of the universal cover phi tilde that is represented by a path which is generated by positive definite matrices, so let's say those positive definite matrices are S, then I can upper bound the rotation number of that element of the universal cover by the integral of the trace of those matrices S. And there might actually be a constant factor missing here, but there's an upper bound up to maybe a constant multiplicative factor that I might be missing. Okay, so basically when you have kind of a positively moving element of a path of symplectic matrices, there's a way of upper bounding the rotation number just using kind of the generators of the path. So then the next observation is that the linearized flow of a Hamiltonian, the Hamiltonian HX, for example, is generated by the Hessian of that Hamiltonian in the sense that I discussed just now. So by applying the trace bound, we can deduce an upper bound for the Ruelle invariant in terms of a certain integral. So here, this is this first lemma. So the Ruelle invariant of a convex star-shaped domain X inside of Cn is bounded above by the integral over X of the Laplacian of the canonical Hamiltonian times the symplectic measure. So, and this is really nice because basically this says that the Ruelle invariant is upper bounded by some kind of curvature integral. The curvature integral here is this Hessian, or this Laplacian thing. Okay, and then so the current proof in our paper then goes like this. There might be a little bit of an improvement made perhaps to this kind of argument, but basically, so by direct analysis of this Laplacian integral, you can show that if you have like a sandwiched pair of convex domains, so you have like a convex domain X sitting inside of a convex domain W, sitting inside of a scaling L X of the original domain X, then these Laplacian integrals actually also sandwich with respect to a constant, depending on the dimension and depending on L. So yeah, so if I can sort of sandwich two convex domains between each other, then I can control the integral of this Laplacian term in terms of I can control their two Laplacian terms in terms of each other. Okay, so in order to use this kind of sandwiching property, we note that if I have any convex domain, then it's always, by kind of a version of the John ellipsoid theorem, affine symplectomorphic to there's no affine symplectomorphism in this statement. But anyway, so if I have a convex domain, then after applying some affine symplectomorphism, I can assume that it's sandwiched between, that it sandwiches some ellipsoid E, where the scaling factor here is 2n. So that means X fits inside of E and E sits inside of 2n, a 2n scaling of X. And so now to prove this Ruelle bound, all I have to do is say, okay, well, first the kind of, so the systole times the Ruelle invariant is bounded above by the systole times this Laplacian integral. And then this Laplacian integral, this Laplacian integral is bounded above by the Laplacian integral for an ellipsoid multiplied by some constant. And then I can upper bound that whole thing. And then, on the other end, and the same kind of, and the reverse kind of thing is true for the ellipsoid. So the volume of an ellipsoid is bounded above by some multiple of the volume of X, where the ellipsoid is the one appearing in this John ellipsoid theorem. So this reduces to, so basically by using the John ellipsoid theorem, I can reduce, and this kind of curvature thing, I can reduce the inequality that I want to prove to proving some inequality between the systole times this curvature integral and the volume for just the case of ellipsoid. So I just have to prove that case. In that case, you can just check explicitly, like you just calculate everything. You can just check that it holds. Yeah. So just to summarize, basically the way you prove this is you just first replace the Ruelle invariant with some integral of Laplacian. Then use the John ellipsoid theorem to reduce the problem to some inequality for ellipsoids, where you can just explicitly prove that it holds. Okay, so now I'll conclude the talk with a discussion of how you use this to solve this dynamical convexity and convexity problem. Okay, so let's say you have okay, so first of all, I'll talk about the problem a little bit. So convexity has a lot of dynamical implications. So for example, this Viterbo conjecture that I talked about, that I alluded to earlier. But there's no definition in terms of purely symplectic terms. So there's sort of no answer to the question, what does it mean for something to be symplectomorphic to a convex domain in sort of purely intrinsic symplectic terms. So one candidate answer to this question, which was introduced by Hofer, Wysocki, Zander in dimension 3, is the following. So a contact form on the boundary of, or on the standard contact sphere is dynamically convex if the Conley-Zander indices are all bounded below by n+1. So if the Conley-Zander indices of every Reeb orbit are bounded below by n+1. And a star-shaped domain X is dynamically convex if the boundary is. So it's very simple to check that a strictly convex domain is dynamically convex. And the question, and I think if you kind of replace the Conley-Zander next to the lower semi-continuous extension, then you can check the same thing for just regular convex domains, not without the strictly thing. However, the converse of this statement, so the statement that dynamically convex implies convex, remained open for a long time. There was a lot of evidence that it wasn't true, but there was kind of no way of detecting counterexamples. And so now, using this Ruelle invariant stuff, we can construct examples of dynamically convex toric domains which violate this Ruelle bound that I proved earlier. Okay, so this is so our original paper in dimension 3 sort of used this very complicated open book construction. And one of the nice things about this Dardanus, Gut, Zhang paper is that they have a really beautiful toric construction of counterexamples, which is extremely simple. So I'm really happy with how simple this family of examples is. And it kind of generalizes very cleanly to higher dimensions. So that's the one I'll talk about today. Okay, so the first thing I need to say to explain this counterexample is I want to consider the following kind of specific convex domain. So I take a very flat ellipsoid, where basically an ellipsoid which is like really long in almost every direction, but then really skinny in one direction. So I'll call this ellipsoid delta A, and here's its moment region. So by the calculation of the ellipsoid Ruelle invariant from earlier, the Ruelle invariant and the volume and is just given by this formula, and then the volume can also be computed as 1 over A. And in particular, you could see really easily from these formulas that the Ruelle invariant of this kind of ellipsoid diverges, but the volume converges to 0. Of course, this is not going to be our counterexample because ellipsoids are convex, but this is kind of the starting point for our counterexample. Okay, so now to actually make our counterexample, let's say that omega is any concave star-shaped moment region. So I take any like a concave moment region is one where the complement inside of the positive orthant is convex. So here I drew a picture of a concave domain in R3. So notice that it's a shape whose complement is convex in the positive orthant. And then so the next thing I want to do is I say omega of epsilon is a new concave domain where I take the union of omega and this very flat ellipsoid region that I described before. And I basically just take the union of their domains and then I smooth it in the region where the union is not smooth. So there's some neighborhood of the place where the boundaries intersect where I have to kind of correct stuff. But I can do that in a way that where such that omega of epsilon remains concave. Okay, and now the theorem is that for any epsilon and any c, there exists a choice of A, so that first of all the systole of x omega is less than or equal to the systole of x omega A. The Ruelle invariant of x omega A is bounded below by the constant c, and the volume of x omega is very close to the volume of x omega c A. They just differ by epsilon, or by quantity bounded by epsilon. Okay, so basically this family, so if I take this, if I take any concave domain and do this kind of modification of unioning it with a super flat ellipsoid, then that operation, if I take the ellipsoid to be flat and long enough, will make the Ruelle invariant diverge, and while the volume and the systole stay the same. So this is exactly the kind of behavior that I want if I want to violate the Ruelle bound that I described earlier. Okay, and so the proof, first of all, is that for concave toric domains, the minimum action and the volume are both monotonic under inclusion of moment regions. So that immediately gives us the first kind of inequalities for the volume and the minimum action that I wanted. And then the second thing is that, so the Ruelle invariant of the kind of modified domain omega A is roughly the Ruelle invariant of the original domain plus the Ruelle invariant of the ellipsoid. This is like something you have to calculate, that they're basically the same to some small error. And then the Ruelle invariant of the first domain is just some number, and the Ruelle invariant of the skinny ellipsoid, as we noted earlier, is some function that diverges with A. So as A goes to infinity, this thing will diverge. And then finally, the volume, of course, the volume is sort of subadditive with respect to union. So if I take the volume of x omega A, that's the volume of, that's bounded above by the volume of x omega and the volume of the skinny ellipsoid. And the volume of the skinny ellipsoid goes to 0 as A goes to infinity. So that part, so that just converges to the volume of the original domain. Okay, so very extremely easy calculation using everything we've done so far to check that these toric examples violate the bounds that we do all the bound violation that we want. Okay, and then the last thing I'll say, which is just the end of this talk, is that so now we just observe that any concave and more generally strictly monotone toric domain is dynamically convex. So so basically not only do these domains break the curvature or the Ruelle invariant bound, but also they are exactly this type of counterexamples we're looking for. They're dynamically convex. So this fact that concave toric domains are dynamically convex is, I guess one reference for it is kind of this Guth-Hutchings paper on symplectic S1 invariant symplectic homology, but we also give an independent proof that generalizes this for strictly monotone toric domains. Okay, and of course, as I've said a couple times already, a corollary of this construction in this lemma is that there exist dynamically convex domains in CN that are not symplectically convex. Okay, and I think that's the entire talk. And thank you, and I'll take questions now.
Thanks, Julian. So yeah, any questions?
I have a question. What goes wrong in the definition of the general Ruelle invariant if the flow is not measure preserving? So is this Ru not going to be L1 or?
Oh, that's a good, so like the fact that I'm going to go backwards to the definition or to the theorem. So the fact that this function little Ru is well defined in L1 is some ergodic theorem.
Is it Kingsman or something like that?
Yeah, it's this Kingman ergodic theorem that showed up in our first paper. So so if it's not measure preserving, then you sort of can't invoke that.
Oh, right.
I mean, it's one interesting thing about this. Our definition of the Ruelle invariant is it sort of decouples the flow from the cocycle. So it seems kind of like not necessarily crucial that the downstairs flow is measure preserving, but you certainly can't prove that this function is well defined otherwise, as far as I know. One thing I will say, which is kind of neat, is that this is an axiom that I didn't state here, is that also the Ruelle invariant is sort of like additive with respect to measures. So if you add two measures together, then the Ruelle invariant is sort of adds. So it's really like some sort of linear function on the polytope of invariant measures. And I think that's a really interesting way of thinking about it, because it sort of begs the question of what other special properties does this thing have when you're, for example, convex? If you think about it more generally as sort of this function of invariant measures.
Wait, but then you need your downstairs flow to preserve both measures, or?
Yeah.
Okay.
So for example, you could have the kind of delta measure on a Reeb orbit, and that would be a perfectly reasonable thing to take the Ruelle invariant of, and it just recovers some sort of mean rotation, mean Convex-Zander next thing.
I also have a question. So the way that you define unit trivialization, right? So it's only defined for context structures that satisfy C1 equals 0. Right?
Yeah, everything is only defined when C1 is 0.
Okay.
May I ask you, so in principle, one can talk about convex tubes and cotangent bundles. So there might be in cotangent bundles kind of counterpart of the whole story.
Yeah. I have definitely, this is something I've like thought about like in passing, but I haven't really proven anything yet. But I actually think it's a really interesting question. Is there anything special you can say and analogous to this Ruelle invariant bounds for like for geodesic flows with some curvature assumption that you could use this for a similar purpose? That's a great question. I think that's a great question. Yeah, so one thing I will say is that this sort of curvature formula, this Laplace integral estimate, is like something that admits a massive generalization. Like you can really generalize this to like any domain in any like Liouville domain inside of a like a Stein manifold satisfying some curvature properties. Like there's this like Ruelle invariant, the kind of curvature estimate here is sort of this very, very generalizable, but this sandwiching property where you can use the John ellipsoid theorem to get like general systolic inequalities is sort of a little trickier because you don't really have a John ellipsoid theorem in more general spaces. Like I sort of don't know what the John ellipsoid theorem would be, for example. I mean, I guess maybe there's some fiber-wise John ellipsoid theorem in cotangent bundles, but in general, I kind of don't know what the John ellipsoid theorem is supposed to be in an arbitrary Stein manifold. Anyway.
Thanks.
Questions?
Sorry.
Yeah.
Yeah, sorry. Can you hear me? Or
I can't.
Okay.
Yeah, sorry.
Sorry, my question was, what can you say about this constant C of n in the I guess it's in the previous slide.
Yeah. So this one.
This one, yes.
Yeah. So that's a great question. So the constant that is currently in our draft is very bad, like very, very bad. It's worse than the constant in our three-dimensional paper, I think. Now, so Michael Hutchings, who's here, actually suggested an improvement to this, which I need to talk to Michael about if we could incorporate that into the draft or not. But basically, the constant's pretty bad, I would say, and like I really have no idea what the ideal one is.
But do you expect that there is something that doesn't depend on dimension, for instance?
No, definitely not.
Okay.
No, okay. I think that should probably. Yeah, I mean, one thing that I should probably do is do more experiments with toric domains, because that's kind of the only case where we can really calculate everything. My instinct is that this n should really depend on the dimension, but I'm actually this constant should depend on the dimension, but I'm actually not entirely sure. It's possible that there's some Viterbo type thing here where it's
that's what I had in mind.
Yeah, it's true. Yeah, I should think more carefully about that, because I'm not totally sure what the right thing to say there is.
Okay.
Yeah.
Thank you.
Do you have an example for star-shaped domains in which this Ruelle invariant is not monotone?
Well, like where inclusion isn't.
Yeah. Like.
Yeah, I think you can actually. Yeah, I mean, I think you can cook up some toric examples where that doesn't happen. I would have to think about.
I think with ellipsoid embeddings, four-dimensional ellipsoids, so the Ruelle invariant just A plus B, but when you can embed an ellipsoid into another, it's very complicated. So.
Oh yeah, right.
Yeah. Like you could just, that's a good. I mean, so monotone. Yeah, I guess the other question is monotone. Like monotone with respect to any symplectic embedding, right?
Mm-hmm.
Is that what you're asking?
Yeah.
Yeah. Then I think what Michael's saying is probably the simplest source.
Mm-hmm.
Yeah, I actually, Michael knows more about the embedding story, the embedding side of the story than I do. Like I haven't really thought about using the Ruelle invariant for any serious embedding obstruction thing. So.
So there is some monotonicity if you have two things of the same volume.
Yeah.
At least for toric to me. So it's one of the little tiny things in my paper.
Yeah.
I played around trying to make a capacity of the Ruelle invariant. It didn't succeed. So I don't know if it's possible.
Mm-hmm.
Okay, I think we're gonna just stop here with comments or questions, and thank Julian again, and leave any other things for the discussion afterwards. So thanks,
Cool.
Julian.